Hello guys, good day and welcome to today's lecture. I am Udom Philemon of Genius Creed. In today's lecture, I'll be showing you guys how to simulate a shortcut distillation column. Now, a shortcut distillation column is mostly used in processes where you want to simulate a distillation column, but you don't want to specify so much. You don't want to have so much to specify, like in the rigorous distillation column. You just want to specify a few things and still get results, right? So that's where you use this shortcut distillation column. According to the Hysys help, the shortcut distillation column works based on the Fenske-Underwood equations, which would help us in determining minimum number of trays, the actual number of trays, the minimum reflux, etc., based on the specifications we make during the simulation. So in this tutorial, we'll be simulating a simple process in order to illustrate how the shortcut distillation column works. Let's get into it. Okay, so this is our simulation problem, which is a mixture of benzene and toluene, right? And then the feed mixture consists of 40% benzene and is 50% flashed. We have a basis of 100 kg per hour and an initial pressure of 760 with our fluid package being Antwine. So we can start the simulation already. Okay, so first off we'll be adding our components. Then our fluid package is Antwine. Okay, so we can get over to the simulation environment. Okay, so we have a feed mixture containing 40% benzene, which is 50% flashed at a pressure of 760 mm². So first off, we can start by specifying our feed. Okay, so the problem statement said that the feed is 50% flashed. What it means is that 50% of the mixture is in vapor phase, and that means the vapor fraction of the mixture would be 0.5. Now, based on the fact that we are specifying vapor phase fraction, we won't be specifying temperature. So we'll specify pressure and then the molar flow rate. (760 mm²), then 100 kg/mole, 100 kg/mole per hour. Now, why we are not specifying temperature is because now that we have specified vapor phase fraction, if you still insist on specifying temperature, the specifications would become over specified, right? So that's why we are not going to be specifying temperature. So we go over to specify the mole fractions. The problem statement says benzene is 40%, which will amount to 0.4 for benzene and 0.6 for toluene automatically, because it's a binary mixture. Okay, so we have specified our feed stream, so we can go ahead to bring in the shortcut column into the simulation environment. Now the shortcut column can be found in the separator section of the model palette. You can see my mouse, my cursor is at the bottom left of my screen. So we are getting out the shortcut column, which we can easily specify. Now this is what the form looks like. So we are attaching our feed to inlet. Then for the shortcut column, we are going to be specifying both condenser and reboiler energy streams, which we can assume as Q1 and Q2 respectively. Then for distillate, our distillate will be the lighter component in the feed, in this case benzene. Then our bottom will be toluene. Enter. So at this point, this is what your shortcut column looks like, still practically under specified, but that's about to change very soon. Okay, so we continue with our specifications. We go over to the parameters tab. So in the parameters tab, this is where we'll be specifying the remaining details. We can start with our condenser pressure and reboiler pressure. Now from the problem statement, condenser and reboiler pressure are 0.2 and 2 atm respectively. Okay, so we have 0.2 and 2 atm respectively. Then our reflux ratio says determine the equilibrium number of stages that will be required for this process if a reflux ratio of 3 is used. So our reflux ratio is 3. Our reflux ratio is 3. So next step will be to specify the component section, which consists of the light key in bottom and the heavy key in distillate. So back to the problem. It says a top product consisting of 2% toluene is desired. Determine the equilibrium number of stages that will be required for this process if a reflux ratio of 3 is used. So now in the distillate portion of the column, the distillate product, 2% toluene is required, which means that benzene at the top will be 98% automatically, since it's a binary mixture, right? So that is what we'll be specifying at this point. So back to it. So for now, the light key in bottom actually means the light component in the bottom, while the heavy key in distillate means the heavy component in the distillate. Now the light key or the light component in this particular problem is benzene, while the heavy component or the heavier component is toluene, right? So we'll be specifying the amount of both of them in the distillate and bottom respectively. Now for heavy key in distillate, we need just 2% of toluene in the distillate, right? So you specify toluene as the heavy component, and then you specify the amount, which is 0.02. Also we'll be doing same for the light component in the bottom, which is benzene, and we'll also be specifying a mole fraction of 0.02. Yes, so that's it. So at this point the shortcut column has solved completely, right? So we can now check details that have been determined by Hysys. Let's go back to parameters. So Hysys calculated the minimum reflux ratio as 2.081. Then we can now check other details from the performance tab, right? So from the performance tab we get the minimum number of trays, which is approximately 8, the actual number of trays approximately 15, and then the optimal feed stage, which is the 8th stage, right? And then other details that may actually be necessary, the condenser duty, the boiler duty, etc. So now to solve this problem, our number of stages based on the calculation done by Hysys is actually 15, which is the actual number of trays. So 15 trays will be required based on our initial specifications, right? And so that's it. This is actually the end of this particular simulation, right? We have simulated a shortcut distillation column. So at this point we have come to the end of this video, right? So I expect comments from you. You drop comments in the comment section, to like the video, and then for those that have not yet subscribed, you can do so in order to get notifications from us in the future. Thank you everyone. See you next time and have a good day.